we are currently discussing the topic of phase diagram, and we have in particular now discussing a eutectic phase diagram. So, yesterday we took the example of lead tin system, which is a eutectic system, and we talked about the eutectic composition and eutectic alloy. Two related terms are there, hypoeutectic and hypereutectic alloys, which also we should be familiar with. So, recall the lead tin phase diagram, which is something like this, shows a minimum in the liquidus at 183 degrees Celsius, which we call the eutectic temperature. In particular, this minimum liquidus point is an important point in the phase diagram, and this is called the eutectic point. Eutectic point, and the temperature corresponding to this is called the eutectic temperature, that is 183 degrees Celsius, the eutectic temperature. I am writing it as TE, and the composition corresponding to this is the eutectic composition. I am calling that CE, and we saw yesterday this was 62 weight percent tin. The alloy of exactly eutectic composition, that alloy is called the eutectic alloy. So, this alloy I am drawing a vertical to represent that composition, it is not a boundary on the phase diagram. This is a eutectic alloy. Eutectic alloy. And then alloys with composition less than the eutectic composition, they are called hypoeutectic alloys. Hypoeutectic alloy means alloy with composition less than the eutectic alloy. Alloys with composition higher than the eutectic alloy are correspondingly called hypereutectic alloy. This will be the hypereutectic alloy. Now, the question is how the microstructure evolves. We have seen how the microstructure evolves for a eutectic alloy. Since eutectic alloy is liquid right up to the eutectic temperature, and then solidification begins at the eutectic temperature, and below eutectic temperature it is a mixture of two phases alpha plus beta, and above that it was liquid. So, liquid solidifies directly into two phases alpha and beta, and we saw yesterday that the eutectic alloy gave a microstructure which was alternating plates of alpha and beta oriented differently in different regions of the microstructure. This is the eutectic alloy. You have alternating plates of alpha and beta. This particular microstructure is called eutectic mixture. It is a mixture of alpha plus beta phase. So, eutectic mixture is not a phase, but a mixture of two phases. So, sometimes it is called a micro constituent. So, this is not a phase, but a micro constituent. Sorry, I am going out of the, So, microconstituent. So, that was for eutectic alloy. Now, the question is how the microstructure evolves for, let us say, a hypoeutectic alloy or a hypereutectic alloy. You can quickly see, if I take a hypoeutectic alloy, so let us take a 40% alloy as our an example of a hypoeutectic alloy. So, this particular alloy, which has an alloy composition of 48% tin, and since this is less than the eutectic composition of 62, this will be a hypoeutectic alloy. This alloy, as it cools, you can see it will not directly form the alpha plus beta, because before it reaches the alpha plus beta region, it enters in the liquid plus alpha region. So, as soon as it hits the liquidus at this temperature, alpha starts forming, and as it gradually, if you cool, then you will draw tie lines at lower temperatures. So, if I draw a tie line at this temperature, more of alpha will form and the amount of alpha will be given by the opposite lever arm, that is this much. So, as you cool, more and more alpha will form, and this process will continue till it reaches the eutectic horizontal. So, let us continue this discussion on a different diagram. So, we are considering this alloy, 40% alloy, which is our hypoeutectic alloy. The phases in this diagram, you are knowing, that is liquid, alpha, alpha plus beta, is liquid plus alpha, liquid plus beta, and beta. So, at the liquidus temperature, or rather just below it, the first solid starts to form, that is alpha starts to form. So, let us try to draw a microstructure corresponding to that. So, you had liquid and just some alpha started to form, and as you will lower the temperature, more alpha will form, and you can see that the maximum amount of alpha will be just above the eutectic temperature. So, at a temperature just above the eutectic, where I have drawn this red tie line, you will have the maximum amount of alpha forming. So, let us make more alpha to represent this situation. So, this is all alpha, and the remainder of the alloy is liquid. Alpha and liquid. So, this is a situation just above the eutectic temperature, which I am calling TE, which for this diagram is 183 degrees Celsius. So, just above the eutectic temperature, we have maximum amount of alpha which has formed, and the remaining is liquid. But the question is, as we cool further, what will happen to this alloy? So, what will be the microstructure just below TE when we cool it? So, you can see just below TE, all liquid should disappear, because the equilibrium phase is only alpha plus beta. Beta has not yet appeared. So, this means this liquid should now transform to both alpha and beta. and that is because why it will transform to both alpha plus beta. Let us first look at what is the composition of this liquid. We are at a temperature just above TE, how the composition of the liquid was evolving. Initial liquid was of the same composition of our alloy composition, which was 40, but when you hit the liquidus and cooled further, then the equilibrium composition of the liquid is given by the tie line, and it started evolving as the liquid end of the tie line gives you the liquid composition. So, initially it was 40, but then it started increasing and it started following this liquidus line. So, this is the evolution of liquid composition, how the liquid composition evolves. So, finally, just above the eutectic temperature, the liquid composition will reach exactly the eutectic composition Ce, which is 62 weight% 10. So, which means this liquid just above TE is exactly of the eutectic composition. The composition is exactly eutectic composition and it is exactly at the eutectic temperature. So, on cooling, this liquid will undergo the eutectic reaction which we have discussed, that a liquid of eutectic composition, if it is cooled at eutectic temperature, it will transform into mixture of alpha and beta. So, if I now try to draw the microstructure just below T, just below the eutectic temperature, then whatever alpha has formed, that will remain. So, I am trying to copy the alpha which I have drawn in that diagram, but what I had drawn as liquid now will transform, that liquid will transform into a mixture of alpha and beta. So, it will transform into eutectic mixture which we had talked about. So, in this alloy you now can see that there are two kinds of region. One region is these alpha which formed before the eutectic reaction. So, they had already formed above TE. So, because of this they are called pro-eutectic alpha. Pro-eutectic alpha, and the remainder of the alloy, this region is eutectic mixture. Eutectic mixture alpha plus beta. So, the pro-eutectic alpha and the eutectic mixture are the two micro constituents of the alloy. So, this and this are micro constituents of hypoeutectic alloy. So, notice that we are using two kinds of terminology. If I say what are the phases in this alloy, I will say phases are alpha and beta, but if I say what are the micro constituents of this alloy, then the micro constituents are pro-eutectic alpha and eutectic mixture, because in microscope, in an optical microscope, you can see pro-eutectic alpha and eutectic mixture distinctly. So, this terminology microconstituent is common while discussing the microstructure and phase diagrams. So, let us look at how to determine the microconstituent of the given alloy. So, if you wish to determine the microconstituents, so remember we had alloy, and we had some pro-eutectic alpha, and we had eutectic mixture. Pro-eutectic, pro-eutectic alpha, and this is eutectic mixture. So, we can ask for example that how much pro-eutectic alpha and eutectic mixture is there in the alloy. Remember that the pro-eutectic alpha formed just above the eutectic temperature. It formed in the range liquid plus alpha, and the maximum amount of it is just above the eutectic temperature. So, to find the amount of pro-eutectic alpha, we have to take a tie line which is just above the eutectic temperature. So, let us note that to determine the microconstituent, we draw the tie line in the two phase region just above the eutectic temperature Te. And then of course, our alloy composition which we had selected was 40. So, that is the fulcrum of our lever, and then the pro-eutectic alpha which we want to calculate. So, the fraction of pro-eutectic alpha in the alloy is nothing but fraction of alpha just above Te. So, we have drawn our tie line just above Te. So, this fraction, so alpha just above Te, remember this is the alpha phase which is on the left hand side of the lever. So, the right hand arm of the lever will represent the fraction of alpha. So, that in our diagram is 62 minus 40 divided by 62 minus 18. Happily it comes out to be nice numbers. So, this is 22 by 44, it is exactly 0.5. So, this means 50% of the alloy will be in the form of pro-eutectic alpha, and the remainder of course will be the eutectic mixture. So, the fraction of the eutectic mixture will be 1 minus the fraction of pro-eutectic alpha, which will also be 0.5. So, in this 40 weight % tin alloy, we expect to find 50% pro-eutectic alpha and 50% eutectic mixture. Recall that the fraction of pro-eutectic alpha is not the fraction of total alpha in the alloy, it is only the fraction of alpha which is as the pro-eutectic phase, because in the eutectic mixture also, eutectic mixture is a mixture of alpha plus beta. So, total alpha in the alloy will be more than the amount of pro-eutectic alpha. Total alpha is some of it is pro-eutectic alpha and some is part of the eutectic mixture. So, then you may like to know what is the total alpha and total beta in the alloy. If you wish to do that, then you have to apply the lever rule just below the eutectic temperature. Let me draw the diagram. So, this is 18, 62, 97 alpha liquid plus beta, and this is alpha. This is 327 and this is 232. So, we are familiar with this diagram by now, and all I am saying that we are talking of a 40% alloy, a hypoeutectic alloy, and we want to know what is the total alpha and total beta in this alloy. If we want to find total alpha and total beta, we draw a tie line just below the eutectic horizontal in the two phase field alpha plus beta. So, to determine total alpha, in the alloy, we draw the tie line just below T. Remember, so when we wanted the micro constituents, we drew the tie line just above T. Now we are interested in total alpha and beta, which are the phases. So, we are now looking at phases in a hypoeutectic alloy. So, once you realize that now since we want total alpha and total beta, we have to take a tie line below the eutectic, because that is where we have alpha and beta, and if we draw a tie line like this tie line does not distinguish between pro-eutectic alpha and eutectic alpha, it will give you total alpha. So, once you recognize this, it is easy to calculate. Now, we are quite familiar with your lever rule. So, we want total alpha, the lever is this red line and the fulcrum is at the alloy composition. So, and alpha is on the left. So, the right hand lever arm is the alpha arm. So, which becomes 97 minus 40 is the lever arm corresponding to alpha, and 97 minus 18 is the total lever arm. So, this gives you 57 by 79. So, that is about 0.72. So, 72% of the total alloy is in alpha form. if total beta will be 1 minus 0.72, that will be 0.28. So, 28% will be total beta. Sometimes one wants to know how much is the eutectic alpha. Note the microstructure that you have alpha in chunks, but you also have alpha as alternate plates. But now that since you have determined total alpha and you have also determined the eutectic, the pro-eutectic alpha, so you can find how much alpha is part of the eutectic mixture. So, if we are interested in that number, that how much of alpha is part of the eutectic mixture, we can call that eutectic alpha, f eutectic alpha. So, since the total alpha is divided in as pro-eutectic alpha and the eutectic alpha, so this is pro-eutectic alpha and the alpha which is part of the eutectic mixture, this will be eutectic alpha. So, this we can simply find as difference between total alpha and the pro-eutectic alpha. We have determined total alpha here as 0.72 and the pro-eutectic alpha as 0.5. So, we take the difference of the two. So, we get 0.22 as the eutectic alpha. So, if we are interested how much alpha is in the eutectic mixture, so that is 22%.